I will be going over the basics of vectors in this video. So here's a definition. A vector is a quantity that contains a magnitude and a direction. Some common vectors are velocity, acceleration, force, and wind speed. So magnitude and direction. So think about wind speed, for example. A weather person might say, the wind is blowing 25 miles per hour out of the west. Okay, so by saying that, we have a magnitude, how strong the wind is, 25 miles an hour, and we have a direction, out of the west. So vectors are different from quantities called scalars, because scalars are simply magnitudes with the appropriate units, spelled units wrong there, such as length, area, and volume. So for example, if we were talking about how big a swimming pool was, we might say it's 5,000 gallons, but we wouldn't say, or 5,000 cubic, I don't even know, meters, or that seems pretty big. It's a huge pool. But anyway, we don't have a direction when we're talking about the size or the volume of that pool. We just say how large it is, so only magnitude for scalars. And then it says, we can represent a vector geometrically as a line segment with an arrow. The arrow specifies the direction, and the length describes the magnitude. So for example, if we have a vector that looks like this, we can call this the initial point. Sometimes it's called the tail. And then we would call this point up here where the arrow is the terminal point. That's sometimes called the head. And so the magnitude is just the length of this. That's called the magnitude. Okay, and then this vector has an angle. Usually we reference this to the positive x-axis, so the angle would be here. Okay, so that line with an arrow is the vector. It has an angle and it has a magnitude. When we want to add vectors, there's a couple ways we can do it. The first way is geometrically. So suppose I have this vector, let's call it vector v, and then I have, let's say, vector w looks like this. Okay, so if I wanted to add these, all I would do is I would take vector v. Okay, so I'm just shifting it down on the screen here. And then I would take vector w and I'd put it the tail of vector w to the head of vector v. Okay, and then to add them, I would draw a new vector from the tail of vector v to the head of vector w. So that would be vector v plus w. So this vector here is could be called a resultant vector. Okay, it's just the result of adding these two vectors together. Now, adding vectors geometrically, it's hard to be precise, especially if we're just drawing a white screen or white page. So we want to be able to do this, also be able to do this algebraically. All right, so to add vectors algebraically, suppose we have two vectors v and w. To add, all we do is we combine the like components. So what we mean by that is vector v, suppose that vector is 2, 3. Vector w is -4, 1. What this representation means is in vector v, 2 is the horizontal component, 3 is the vertical component. In vector w, -4 is the horizontal, 1 is the vertical. Now what this means is that if we were to draw vector v, we're going to go 2 units in the horizontal direction, 3 units in the vertical direction, and that vector would look like this. That's vector v. Vector w, I'm going to go -4 in the horizontal, we go 1 in the vertical, so that vector is going to look maybe something like this. Okay, so we want to add these together. Adding these together, I'm going to figure out what the resultant is. And what it's saying up here is we just want to combine the like components. So to add these, all we do is we add the horizontal components. So this is going to be 2 plus negative 4 is negative 2. 3 plus 1 is 4. So that would be vector v plus vector w. And if we were to graph that, well, negative 2 is here, 4 is up here, so that resultant vector would be something like this. All right, let's do some other simple arithmetic with some vectors. So the first example, we want to find v minus w, and we're given these two vectors. So all we do to find this v minus w, we're just going to combine the like components. So v minus w, so I'm going to say negative 1 minus 2, so minus 1, or oops, negative 1 minus 2 for the horizontal component. And then for the vertical component, we're going to say 2 minus negative 3. Putting that all together, I end up with negative 3 comma 5. So that would be v minus w. The second one, we have 3 times vector w. So vector w is 2 comma negative 3, so we're going to say 3 times 2 comma negative 3. I don't know if we need the parentheses there, but so it's kind of like we just multiply 3, which is a scalar. It's just a magnitude. There's no direction associated with 3. We just multiply that scalar by each component. So what we end up with is 6 comma negative 9. For the next one, I have 4 times vector w and 5 times vector v. Okay, so I just multiply the scalars out. I get 8, negative 12, plus negative 5, 10, and then combine the like components. So I'm going to have 8 and negative 5 gives me 3, and then negative 12 plus 10 is going to be negative 2. So that would be that vector addition there. And then this fourth one is slightly different. These, it's kind of like two absolute value symbols. What that means is we want to find the magnitude of this this vector inside here. So it's just asking us for the length of this vector. So the first thing we're going to do is we're going to find what's happening inside the magnitude symbol. So 3 times vector w, which is 2 comma negative 3, minus 2 times vector v, which is negative 1 comma 2. So working this down, I get 8 comma negative 13. So to find the magnitude, well, what this is saying is we have a vector. The horizontal component is 8. The vertical component is negative 13. So that vector is like this. So in order to find this magnitude, let's call it r. We're just going to use the Pythagorean theorem. So I'm going to have 8 squared plus negative 13 squared is equal to r squared. So we have square root of 64 plus 169 is equal to r. So r is going to come out to 233 square root. So that's the magnitude of this initial vector. All right, and then one last example here. This time we're writing the vectors in a slightly different format here. But all that this means is vector u is equal to 4 comma 7. So 4 is the horizontal, or 4i, that's saying 4 in the horizontal direction. 7j is saying 7 in the vertical direction. Okay, so that's what that means. All right, so v, we could similarly write it as 2 comma 5. And then the question says, what is u minus 3v? Okay, so I think sometimes this is maybe easier for students when it's written in the ij form. So vector u, we're going to say 4i plus 7j minus 3 times vector v. This seems even more algebraic. 4i plus 7j minus 6i minus 15j, and then just combine like terms. So we get negative 2i minus 8j. That's that vector, so u minus 3v. And then the second one here, we want the magnitude of u plus 2v. We end up with 8i plus 17j. And then the magnitude, again, it's like 8 in the horizontal, 17 in the vertical. So we want to know how long that vector is. We're going to say r squared is equal to 8 squared plus 17 squared. Solving for r, we end up with r is the square root of 353. So lastly, we want to be able to express a vector in terms of its magnitude and direction. So we have a definition here. Let vector v have components v1, v2, and that's a position vector. And suppose theta is the smallest non-negative angle that v makes with the positive x-axis. The angle theta is called the direction angle of vector v. The length or magnitude of the vector is here. So what this is saying is that if we have a vector that's written in this form, suppose it's vector w 5 cosine 45 degrees I plus sine 45 degrees j. So what this is saying is this vector has a magnitude of 5, and the angle from the positive x-axis would be 45 degrees. So if we draw this, we're going to see that this vector has a magnitude of 5, and this angle here is 45 degrees. So this is just a way of expressing a vector that shows both its magnitude and its direction. And writing a vector in this way is called trigonometric form. Sometimes also this is called polar form. I use both of these expressions, trig form and polar form, interchangeably. All right, let's look at an example. Write the vector of magnitude 3 whose direction angle is pi over 3. So let's call this vector v. So vector v, again, I'm going to write the magnitude of vector v times cosine theta of component I plus sine theta component j. So magnitude of vector v, it tells us it's 3. And then cosine of pi over 3i plus sine pi over 3j. Cosine of pi over 3 is 1/2. So I'm going to have 1/2 I plus sine of pi over 3 is root 3 over 2 j. And then multiplying this out, I get 3/2 I plus 3 root 3 over 2 j. So that would be this vector written in polar form. And what this means is that the angle is pi over 3, the magnitude is 3. So this angle right here is pi over 3. So this right here is telling us what the horizontal component of this vector is and what the vertical component is. So the vertical component is 3 root 3 over 2. The horizontal component is 3/2. Okay, similar example. We're going to have a magnitude of 2 cosine 11 pi over 6 I plus sine 11 pi over 6 j. Cosine of 11 pi over 6, that's quadrant 4, that's positive. So root 3 over 2i plus sine of 11 pi over 6 is negative 1/2 j. Multiplying this out, I get root 3i plus, or rather, it's going to be minus 1j. So we can write it like this. So in order to write this vector, we start in polar form and then multiply it out to get the final form written in components like this. So again, what this is saying is now I'm going to start with this form and see how it matches what is given to us. So root 3 in the horizontal direction, -1 in the vertical direction. So this vector looks like this, okay? And that magnitude is 2, and this angle is 11 pi over 6. And then this last example, is a little different. Now we're given the vector and we want to find the angle, the direction angle for this vector. So to get a visual here, see what we're looking at. So -4, that's the horizontal component. 3 is the vertical component. So the vector looks something like this, and the direction angle is here. Okay, so we can think about this as a right triangle. So this is 3, this is -4. So if we did -4 squared plus 3 squared is equal to, let's call this, I don't know, r. So I have 16 plus 9 is equal to r squared, so 5 is going to equal r. So that's the magnitude. And actually we don't even need to do that, but if I want to find this angle here, what I could do is I could simply use one of the trig functions. So oftentimes we'll say tangent of theta, tangent is opposite over adjacent. Okay, so to figure out what theta is, we're going to do tangent inverse of -3/4, and that will equal theta. So we need to use the calculator here. And make sure your calculator is in degrees. Okay, so when you type this into the calculator, you get -36.8698, so let's call it 0.87 degrees. Now, when we use the calculator and find an inverse, the output value for inverse of tangent is always between -90 degrees and 90 degrees. Okay, so when we type this in, actually, since we have a -36 degrees about, what that's telling us is -36 is down here. Now that does not match up with the image that we drew. So -36.87 degrees, that's in quadrant 4. We want to get into quadrant 2, so what we need to do is add 180 degrees, and doing so we're going to end up with 143.13 degrees. So this final step can be quite tricky, so you need to be careful to make sure that the angle that we actually find from the calculator matches the image and which quadrant we want to be in.